Sorry, I didn't have my program ready. So, great pleasure to welcome Oliver, whose slides are already up on the board. Well, some of them anyway. I'm sure there'll be plenty more. So, Oliver will be telling us about universality and string interactions. Thank you.
Thanks a lot, Lionel, for the kind introduction, and I'm very grateful to all the organizers for the invitation, for the opportunity to speak, and most of all for setting up this inspiring program. I'd like to tell you about universality in string interactions, which is based on a recent paper in collaboration with Huang and Congkao Wen. So the point of view for these interactions to be discussed is the usual relation between string theories and field theories. If you study open and closed strings, no matter which particular string theory, no matter which particular incarnation, you will always land on certain field theories in the massless sector of the spectrum. So the massless states will always contain some Yang-Mills or gravity theory. And if you study a supersymmetric string theory, then accordingly you get super Yang-Mills and supergravity in the massless part of the spectrum. And on top of that, each string theory will have an infinite tower of extras. These are additional modes, infinitely many, and their mass squares, they always scale with 1 over alpha prime being the inverse string tension. And they scale with some integer numbers upstairs. Okay, strictly speaking, I should also allow for -1 in case we consider the bosonic string theory the tachyon. But yeah, let's say these are integers. All the masses go like 1 over alpha prime. And the interactions I'd like to discuss in this talk, these are the effective vertices, which you get in the low energy regime of this setup. So what do I mean by low energy? You often hear the statement that alpha prime goes to 0, and the dimensionless quantity that I'll send to 0 today is the relevant momenta. K square alpha prime is a dimensionless combination, so this you can send to 0 in a meaningful way. So this is what I mean by low energies. And what this means for the interplay of the states is, at low energies, the masses of the extra modes become very large. So these extra modes decouple in the low energy limit, or more precisely, you can think of them as being integrated out. And what you are left behind with is Yang-Mills theory or Einstein-Hilbert plus effective vertices. So the net effect of integrating out the extra modes is a couple of effective gluon and graviton interactions. Just to draw a picture on that, suppose you study a 4-gluon scattering process. Then in the full-fledged string theory, you would propagate all kinds of extra states. So in these internal propagators here, you will find all kinds of masses, like an integer over alpha prime, and it will be an infinity of states that generically contribute. And this low energy limit, this integrating out procedure, means that you resum all of that to give you a big contact vertex of 4-point type. So here's just one arbitrary representative. Among other things, you get some f to the 4th, 4 powers of the field strength, with 2 powers of alpha prime to get the mass dimensions right. And this is just one very simple example. There is, of course, a lot of ... where the ... represent an infinity of extra interactions with more and more derivatives. So this is where the main focus of the talk will be, on the ... Okay, so this is the picture behind these interactions whose universality will be discussed. Let me get a bit more specific. So if you do this for the closed string sector, whoops, then you will receive a couple of modifications to the Einstein-Hilbert action. I'll be extremely sloppy about overall prefactors. That's why I refuse to give you more than a proportionality sign at this place. So in the very low energy limit, alpha prime equals 0, you get Einstein-Hilbert gravity. And then in a generic string theory, you might expect all kinds of corrections, starting with R square, as long as you don't specify your theory. A few words on the notation. Here with this phi, I try to say that these coefficients of R square may depend on the moduli of the theory, like background values of various scalar fields. And as you all know, the VEF of the dilaton is setting the string coupling. So we can think of this as mostly representing the string coupling dependence to keep track of whether we look at a tree level contribution or a loop contribution to that effective operator. Okay, so in this notation there can be more and more curvature corrections with more and more moduli dependent coefficients. A priori, I would write down any operator that is compatible with the symmetries. And certainly, these moduli-dependent coefficients will be very much theory-dependent. So the universality in the title aims to probe some subsectors where the theory dependence washes out. Okay, and I can do the completely analogous expansion for the gauge interactions. Where you take a trace over the non-abelian gauge group of the Young-Mills Lagrangian plus alpha prime deformations, again with some moduli dependence. The first correction that can't be removed by field by definition is f cube, and then it can go on with things like the f to the 4 example that I just mentioned, plus ... of higher and higher mass dimension. Okay, so if you are used to studying the superstring, then you enjoy the protection of maximal supersymmetry. And of course, the first of these corrections that I wrote down, they are then incompatible. The lowest order corrections beyond the field theory actions, they are absent for the superstring. In other words, 16 supercharges don't allow f cube, and 32 supercharges from type 2a and type 2b won't allow for these guys. Good. Now, after having told you what kind of things are zero, let me give you a non-zero example of a theory-dependent coefficient. A very beautiful example is the type 2b theory in d equal 10 dimensions. So this is a theory where a lot more exact results are known than for others. This is where people in the room have contributed a lot. So here this particular C3 example, this is something where I believe Pierre, in collaboration with Michael, I mean the green Goodperle Michaels, has contributed. In beautiful papers from 97, it was shown how to derive exact and non-perturbative statements on the coefficient of r to the 4th, making use of the S duality of that type 2b theory. So one upshot, or one way to summarize the upshot is, along with r to the 4th, you get two contributions of perturbative type. So here you have two inverse powers of the string coupling, which signals a tree-level interaction. This you can reproduce by computing a 4-graviton tree amplitude. And there is a one-loop contribution to be identified from the 0 exponent of the G-string dependence. And that's all there is among the polynomial interaction, power law dependencies. On top of that, you have a couple of non-perturbative dependencies on the string coupling, which go like e to the minus 1 over gs. So these signal instanton contributions. And well, you can anticipate from this kind of dependence, this is the nasty function that not even Chuck Norris can Taylor expand. Certainly there's a well-defined separation between the non-perturbative sector and the two perturbative fingerprints. Okay, so these zetas here will play a crucial role. I'll define them in a second. And to already deliver the spoiler, I'll only study the tree-level part. I'll only give universality statements for the tree-level interactions with this dependence on the string coupling. But to avoid that it's totally boring, I'll probe the ... to arbitrary orders in alpha prime. Okay, so here you have seen some first examples of the theories I want to probe. Type 2a, type 2b is certainly in the catalog. Let me give you the complete list about which universality statements will be made. I'll study two incarnations of the gauge sector. First of all, in the open superstring. And secondly, in the open bosonic string. And as we have heard several times in this workshop, you can double copy the gauge interactions, or at least some specific building blocks of the amplitudes. So the double copies of these open string theories will give rise to different incarnations of gravity. I guess historically speaking, one can say that this is actually the birthplace of the double copy concept, simply because closed string excitations are a double copy of open string excitations. So what do you get by double copying these two ingredients? Two copies of the open superstring will land you on the type 2a or b superstring, where a and b are distinguished by the chirality of the fermions. Then two copies of the open bosonic string. Well, very obviously, this is the closed bosonic string. But you can be more adventurous and combine two different theories to land you on the heterotic string. And actually, this was the starting point for this project when Yutin, Congkao, and I discussed via email some parallels between heterotic string actions and type 2 actions to probe possible counterterms that are compatible with 16 or 32 supercharges. Okay, so the universality statements will be about effective operators that occur with the same coefficients in all of the three for gravitational interactions. And all of this will be derived from the open string square root. So in an earlier part of the talk, I'll show you some gauge interactions that appear in both of these with the same coefficients. Now, you could ask me about the gauge sector of the heterotic string, which would be standing here. Also, this is certainly a quite interesting theory, but it doesn't fit into the universality statements and will therefore not be discussed today. But there are very nice results. Say, among other people, Stieberger and Taylor have studied this in January 2014, where they observed nice relations between open superstring and the gauge sector of the heterotic string, at least in the single trace sector. Okay, I'll often be abusive in terminology. Whenever there is supersymmetry, then all of these symbols represent the supersymmetrization. So Obviously, f to the fourth has a long tail with gay-Gino interactions, and much more is in this r to the fourth. So just to make sure I can use the same notation for all the theories, even those without SUSY, I don't make it explicit that fermions are understood to be included. All right. So let me proceed to telling you the main results. What will happen in this talk? As I said before, the big disclaimer is only tree-level interactions will be discussed, whose string coupling dependence goes like this. And within this tree-level interactions, I will identify universal operators. Namely, operators, as you see some examples on the neighbor blackboard, gauge interactions. Okay, I should put a trace to be exact. Gauge interactions where you have some power of the field strength, some numbers of covariant derivatives, and all of this decorated by the appropriate power of alpha prime to get the mass dimension right. Okay, and on the gravitational side, the operators of interest will be quite similarly some powers of the Weyl curvature with some number of covariant derivatives acting on that. And yeah, all of this for arbitrarily high powers. Okay, the main claim is such interactions are universal if and only if their coefficients satisfies a certain number theoretic property. You can identify universal operators by looking at the prefactor. If this is a multiple zeta value of the correct weight. So I should define multiple zeta values. These are very interesting periods that appear in various places of quantum field theory and string theory. They take a number of integer arguments and are then defined to be a nested sum. Here I'm summing over positive integers, and what I'm summing is the summation variable raised to some power, to some negative power. So as I said, all the arguments of the multiple zeta values are integers. The last one should better be 2 or larger to avoid the divergence of the harmonic sum. And this weight here that appears in the universality criterion, the weight is defined as the sum of all the arguments. And actually here I'm relying on a couple of mathematical conjectures that the weight is a meaningful quantity. As it appears currently, there is no relation that mixes multiple zeta values of different weights with rational coefficients. So quite importantly, the weight doesn't care if you multiply by a rational number. And accordingly, all of these multiple zeta value relations, they're interesting if the coefficients are rational numbers. Something like you can relate pi zeta 2 to pi squared over 6. And of course, if I multiply this by a rational number, then both sides remain equally interesting. Okay, so in this sense, relying on these mathematical conjectures, you can assign a meaningful weight to any multiple zeta value coefficient that you might meet. Let's check this for a couple of examples. So here are again the lowest order gravitational interactions that might appear. So Einstein-Hilbert has no power of alpha prime and also no multiple zeta value. Accordingly, it satisfies the universality criterion, and indeed, this is the low energy limit of all the closed string theories. Now here, if we look at the first corrections, there is no multiple zeta value along with them, but they don't appear everywhere. As I said, they are incompatible with maximal supersymmetry. Our cube is even that unpopular that not even the heterotic string likes it. So only in bosonic string theory you will find these guys. And here, starting from r to the fourth, there are in fact several r to the fourth couplings. One of them has a zeta 3. That's the example from here. And this is the maximally supersymmetrizable, which you find in the type 2a, type 2b string, and likewise in heterotic and bosonic. But there's a second combination of r to the fourth, which will be made precise later on, that only appears in the heterotic string. And in fact, there are two further ones in the bosonic string. That's why you see 2 check marks here. Okay, and all this to say, this table is meant to give you a flavor of how this universality criterion should be read. Here, there is an exact correspondence between the power of alpha prime and the weight of the multiple zeta value, and accordingly, this is something universal. And okay, the trivial example is here. Whereas all the others, they violate the correspondence between weight and alpha prime power, and, well, correspondingly, you don't find them in all the theories. Okay, so this is the main claim. And we are far away from having a rigid proof. All I can give you is evidence. And this will stem from the study of amplitudes. So for the rest of this talk, I'll speak about tree-level amplitudes and explain how their structure gives rise to this universality claim on the effective operators. So this finishes the introductory part of this talk. The main result you see over there. Maybe I should give it a nice frame. What will happen in the remainder of this talk? I will walk you through the tree-level amplitudes of all the open and closed string theories in the catalog, and will show how certain properties of the amplitudes imply that universality statement. Are there any questions before I delve into the review of the superstring? Oh, the resumation of that. Yeah. Okay, let's say at the end of the day, your question amounts to resumming the superstring interactions for type 1 and type 2.
Or using it in some other way, universality result.
Yeah.
Not yet.
So for the resumation, I can't say that this universality statement can say anything new about type 1 and type 2 in isolation. Right. And the second part of your question sounded like, what do we learn from this?
Well, I mean, presumably you learn if there's another theory, you might know what the answer will be because it might be in the same universality class. I just wondered what else, yes. What
Okay.
you learn.
So the what else, I can only reply with a wild speculation. Given that all the string theories appear to agree on a certain subset of operators, one might wonder if this is some necessary feature of a theory of quantum gravity. This is highly speculative, but maybe there is something particularly good to those universal sets of operators that they are indispensable.
Or that they're all coming from M theory or something. They're all coming from the same place.
I guess, yeah, right. I guess physically speaking, it will probably amount to use of the web of dualities. And in this talk, I'll show a more technical phase of that, namely, they stem from the same moduli space of punctured disks and spheres. But hopefully, there's ultimately a nice connection between the physical picture and the iterated integral picture. All right, so let's look at the amplitudes which are responsible for all these operators. let me start with a review of the open superstring. I'll give you the expression for the n gluon tree-level amplitude. And actually, as long as we are in the superstring, this is a statement about the entire gluon supermultiplet. This is material taken from a paper in 2011 with Carlos Mafra and Stefan Schieberger. We have used the pure spinor formalism to compute the endpoint amplitude for the open superstring. And I should really emphasize, without the pure spinor formalism, this calculation would not have been possible in the way how we organized it. So I believe it was of crucial importance. The finding was this is a color-ordered amplitude which will depend on various gluon and gluino polarizations, ideally packaged in a superfield. And all the polarization in this amplitude you can capture through the own field theory limit. So here we are computing a string amplitude in a certain color ordering, and it will receive contributions from various color orderings of the Yang-Mills field theory. So here I'm summing over permutation sigma that rotate n minus 3 legs in any way you like. This is, by the way, the BCJ basis. So here is where all the polarization dependence resides. If this is, say, gauge invariant and supersymmetric, or PRST invariant in short, then so will be the left-hand side. And it's a field theory quantity. There's no alpha prime in that part. All the alpha primes are sitting somewhere else. For each color ordering here, there is a weighting function, f indexed by the permutation sigma, which tells you how to carry out that superposition. And this is where all the alpha primes are sitting. So here is a central definition. Whenever I say Sij, I mean the dimensionless version of the Mandelstam invariance. Apart from the off-shell momentum square, you put in an alpha prime to keep things dimensionless. So low energy means that you send these Sij to 0. Okay, so this is how the superstring allows you to disentangle alpha prime from field theory building blocks. And I owe you a definition of these capital Fs. So this is the basis of integrals. Not surprisingly, these are iterated integrals over the boundary of the disk worldsheet. And I write you their integral representation now. By certain choices of how to fix the conformal killing group, you can map all the integration variables to the unit interval. After fixing 3 positions to 0, 1, and infinity, there are n minus 3 integrations to be carried out. Then there is the famous Kober-Nielsen factor, which you have seen in several talks from the previous days. The shorthand here is Cij means the difference, Ci minus Cj. Now the most technical part of these n minus 3 factorial bases is coming right now. You don't need to pay attention to all the bits and pieces here. I'm just making sure that a complete definition is on the blackboard. So that permutation, which indexes the integrals here, it shuffles around those pieces of the integrand. Okay, it's some rational function of the Ci minus Cj here, and funnily there's this rigid pattern that there's always the Mandelstam on top of the corresponding worldsheet singularity. Okay, and this is to be evaluated at Z1 equals 0, Cn minus 1 equal 1, and Cn to infinity. Okay, and now my apologies for all of those who try to take readable notes. this was now for a particular color ordering on the string, but I can easily upgrade it to keep the color ordering variable flexible. So I introduce a capital sigma to index the color orderings for the superstring amplitude, and accordingly I have to give the functions here an additional index, capital sigma. Like this, the number of integrals grows to n minus 3 factorial square. And the way how this capital sigma enters, this is the integration domain. I mean, some sort of by definition, if you fiddle around with the color ordering in string theory, you just alter the cyclic ordering of the punctures on the disk boundary, and this is reflected in the integration domain. But here, with this choice of n minus 3 factorial contours, you still remain in the unit interval in this parametrization. And the fact that this is a basis with respect to both, it follows from monodromy relations relating the different choices of capital sigma. And if you fiddle around here, this is the same as BCJ relations. So this is indeed a basis. All right. Let's look at a 4-point example of all this. At 4 points, all the permutation sums, they collapse to a single term. n minus 3 factorial gives you 1 if you set n equal 4. Then the 4-point incarnation of these disk integrals are shown here. This is basically the Euler beta function. And if you are interested in the low energy behavior, there are nice identities for the log of the gamma function. So if you want to see the alpha prime expansion, then please take this exponential here. And as you see, there are the promised multiple zeta values. And in fact, there's a one-to-one correlation between the order of alpha prime and the weight of the zeta value. Okay, in the next blackboard, I'll introduce a couple of matrices to which these above statements apply. But for the moment, I guess it's sufficient to see how the functions behave in the 4-point special case. Right. So let me now come to the low energy properties of these integrals. I pointed out this funny pattern of Sij divided by Zij. I mean, the rule of thumb is that a worldsheet singularity, inverse Cij, gives you a pole in a Mandelstam variable. But the numerator, Sij, which you see right here, it cancels this pole before it can even occur. So the integrand is, if you wish, fine-tuned such that the f's are analytic. The f's don't have any poles in the Mandelstam variables. Putting it differently, all the poles in the endpoint tree are sitting in these Yang-Mills factors. Admittedly, there are a couple of poles which are not compatible with the ordering over there, so this is the job of the functions to cancel unwanted poles. But for sure, they won't add any poles. Okay, so let me give you a flavor of how this alpha prime expansion might look like. If you like, you can look at the 4-point example over there as a guideline or to get some intuition of what I'm writing here. So far, it's a couple of definitions. There will be some zeta 2, zeta 3, zeta 4, zeta 5 in these guys, and I just introduce a name for the coefficients. And let's keep in mind, everything is a matrix. Everything is a matrix of size n minus 3 factorial by n minus 3 factorial. So these p's and m's are matrices of that size, and all its entries are polynomials of degree w. So this index here tells you about the degree. In Sij. And most importantly, the coefficients within these polynomials are purely rational. So all the transcendental weight is outsourced or is explicit in this line. All the zeta values that do occur are made explicit in this line here. And by the way, here I'm going to a tentative Q basis. for instance, all the multi-argument zetas at weight 4 are proportional to zeta 2 square. So of course, all the reductions are understood to be already made. And starting from weight 5, there is a two-dimensional Q basis, conjecturally, with these two members. And amusingly, the coefficient of the product is some stuff you have seen before. This is a matrix product between the P2 matrix, defined as the zeta 2 coefficient, times the M3 matrix, defined to be the M3 coefficient. It's a very economic property of the alpha prime expansion. It goes on similarly that at weight 6 there's a new matrix P6, and there is some recycling that the coefficient of zeta 3 square in this basis is the matrix product of the guy you've seen above here.
But P4 is not the matrix product of P2.
I'm sorry?
But P4 is the matrix product of P2.
Oh no, it isn't. It isn't. So matrices that are called differently, they have no relation. Yeah, interesting question. We were expecting that and trying our best to find a relation, but I can't tell you anything qualified on that. Yeah. By the way, these results are taken from a paper with Stefan Stieberger, 1205, 1516. And among other things, it is discussed in this paper how the multiple zeta values kick in. I mean, the definition of the multi-zeta allows for several arguments, and the first time that you can't eliminate them is at weight 8. That's the first irreducible depth 2 multi-zeta. Of course, you can trade it for another one, but in the canonical basis choice, where canonical means that it's the one taken from a data mine paper of Vermaseren et al., in a certain basis choice, the coefficient of this multi-zeta is a commutator of such matrices. Just to give you a little flavor of how this looks at higher weight. Okay, let's compare this with the 4-point case. So here, this 4-point function f2, it defines for you the 1-by-1 matrices in the 4-point case. So the explicit answers for P and M in the 4-point case is this polynomial here, and that polynomial here for the even and odd weight case. And at 5 points, it's something 2-by-2 like with a bit more Mandelstams. Yeah. And a commutator becomes trivial in the 4-point case where everything is scalar, so you don't have any multi-zetas of higher depth in the 4-point amplitude, consistent with inspection. Okay. So, sorry?
Omega is the 3, 4, etc. right? The P omega. W.
W? Which?
W is an integer.
Oh yeah, W is an
2,
integer,
3,
sorry.
4.
Indeed. Okay. So if you want to see explicit data, I can either refer you to a web page or to one of the many methods on the market. There's a huge body of literature on that, and my choice, which one to recommend, might be biased, but an efficient way to compute all of them for arbitrary multiplicity is, I would recommend to use the Drinfeld associator, which is a generating series of multiple zeta values. Also, it is the universal monodromy of the Krzynsznik-Samolotchikov equation, something which governs integrals of this type. So one method to compute these guys you can find in that paper with Johannes Brödel, Stefan Stieberger, and Tomohide Terasoma. So Emil was pointing out that these integrals might be something of hypergeometric type. True, but in the end of the day, when it comes to reading out the alpha prime expansion, all you need is a Drinfeld associator. If you just want to see the data, no need to consult the math book on hypergeometric functions. Okay, and the most important property of these functions, relevant for the universality statements, is the uniform transcendentality. This is just another way of saying, if you look at the coefficient alpha prime to the W, then everything you will find is multiple zeta values at the same weight. One-to-one correlation. And one way to prove it is, well, it's explicit in the Drinfeld associator construction because the associator is well known to satisfy such a uniform transcendentality property. And also, this Drinfeld construction is one direct proof to see analyticity, to see that there are really no poles in the expansion of these integrals. Okay, so like that, we get all the data on the amplitudes, and to connect with effective actions. I mean, the standard process to get from amplitudes to the action is to subtract off all the reducible diagrams. It's a tedious process, but in principle, it is guaranteed to terminate. So accordingly, with everything here, I can identify a part of the effective action. So for instance, this leading term 1 is just saying that you reproduce the Yang-Mills amplitudes in the field theory limit. So this 1 means that you land on the F-square operators you know. Then P2 is encoding the amplitudes or the matrix elements of the F to the 4th operator, theta 2. That's the first effective vertex I drew for you. And accordingly, the M3 matrices, they encode interactions of the next higher order. It's actually a superposition of d square F to the 4th plus F to the 5th. Or if you study the supersymmetrizable operator, which we will get from the superstring, you need both of them. Okay, so you can write down something similar by going through the list of alpha prime corrections. Here, maybe the exciting one, the zeta 3,5, is something of d to the 10, F to the 5th. There won't be any F to the 4th, because it doesn't appear in the 4-point amplitude. And then there's a similar tail of less derivatives, but more field strengths, all the way up to F to the 10th. All right. So this is everything I wanted to say on the open superstring. Are there any questions before I proceed to the open bosonic string?
Are they all universal, or?
Oh yes, the upshot will be all of them, since they satisfy the uniform transcendentality property, they're all going to be universal and also appear in the amplitudes of the heterotic and bosonic string.
Are all maximally supersymmetric amplitudes universal?
Yes. Okay. Having spent that much time on the review allows me to cover the new material rather briefly. About the open bosonic string, the main surprise is that there are no surprises. So if you compute it in the pedestrian way, if you take the correlator of the bosonic string, and if you simplify your integrals using partial fraction and integration by parts, then what you will find, if you do this exhaustively, that you land on the same n-3 factorial basis of integrals. Okay, I haven't given you the examples for integration by parts. Let me just say, in the bosonic string, you need more of them. The superstring is very computational friendly, that the IBP work is, well, enjoyable. For the bosonic string, it's a bit less enjoyable, since there are many integral reductions which confront you with a tachyonic pole like this. So such a propagator signals tachyon propagation, what we expect in the bosonic string. And here I'm giving one example of a tachyon pole containing integral. So the statement over there was you can reduce it to a multiple of F2. Yes, it's a multiple, but there is such a tachyon prefactor in the expansion with respect to the integral basis. If you want to see more details, there is some partial integration on the way, where in the integration by parts you catch this ratio here. Then a bit later there's partial fraction. And okay, I don't want to go into the details, but just give you a flavor of how this integral reduction proceeds. It still fits in 2 lines for this 4-point integral, but it calls for the computer's help in the 5-point and higher point case. So it's more a brute force statement. You can, if you really want to. You can reduce it to the same integral basis we have seen before. So having said that, let me give you the answer for the open bosonic string endpoint amplitude. I'll condense my notation a bit. I don't display the legs anymore on which the permutations act. So this capital sigma, in fact, rotates n minus 3 legs. Okay, and as I said, it will be pretty boring in the sense of the same integral expansion, or the same basis of integrals appears on the right-hand side. But this time, it's not the A. Young-Mills, but something more complicated. So here, this is, again, a kinematic factor, which carries all the polarizations, but it additionally depends on alpha prime. So let me note this. All polarizations. This time, no superfields, of course, since this is the bosonic string with 0 supercharges. And the only good news, the dependence on alpha prime is rational. There won't be any multiple zeta values, as I'll argue shortly. Good. So what else can we say about these kinematic factors B here? It's well known that the low energy limit also for the bosonic string is Young-Mills field theory. So if I now alpha prime expand these guys here, the leading term at alpha prime to the 0th must be A. Young-Mills. Otherwise, you would screw up the low energy limit, the field theory limit. And on top of that, you will get a power series dependence on alpha prime. So formally, you can isolate the coefficient of various powers in alpha prime. Let's call them BK, the coefficient of the kth power in alpha prime. That's something which you can always do. And by the way, the entire object B satisfies the Kleist-Coif and BCJ relations, either the full thing with its alpha prime dependence or separately at each order. So this is another rich source of BCJ satisfying objects. And to show you the very simplest object, at 3 points, the kinematic factor B is, first of all, the Young-Mills tree. And this potentially infinite series only contains one term. The only alpha prime correction at 3 points is, well, the effective action is going to be the F cube operator. And this is its fingerprint on the amplitudes. So that's the F cube interaction. Now, for the 4-point counterpart, I prepared the corresponding B here on this blackboard. In the 4-point amplitude, the coefficient of the F2 function is this guy here. We start with a Young-Mills tree, and here are the corrections. So here I'm packaging all the polarization dependence in gauge invariant objects. So this Fij is just the contraction of linearized field strengths. And the GIs, well, it's a multiple of the soft factor, but with all the poles removed. All this to say, these are gauge invariant and well-known kinematic dependencies. And, well, the integral reduction drives you to very wild pole structures. So my apologies that you can't see manifest locality, but take my word, the worst thing that you encounter is a single pole in the Mandelstam variables. And if you want to connect this with the tachyonic poles to the general expressions I gave to the power series expansion, if you want to know the 4-point incarnation of the BKs, then you just do the geometric series. Whenever you see a tachyon pole, just expand it out. Okay. And here, from this, you can see that the dependence on alpha prime won't involve any multiple zeta values. So here, this is purely rational. This is no MZV, for sure. Okay, and
Contain the double pole and the higher pole. You said it's only single pole. The B function, the 4 points you write down there. The blackboard.
this blackboard or the
No,
other
this
one?
blackboard. They have the denominator have the s1 2 square etc. You said this will be cancelled by
Right. So to B1, the first alpha prime correction, you get contributions from here and from there.
yeah.
So the tentative double poles here will talk to the tentative double poles there, and at the end of the day, it's really a single pole. It's the 4-point matrix element of the F cube operator.
You see the F and G contain the depend on S2.
The G's have one
Okay,
factor of
okay.
S in each term, so there's a lot of cancellation taking place. It's the usual trade-off. If you want to manifest gauge invariance, what I chose to do, you lose the grip on locality. Yeah. Oh, and by the way, this is a permutation invariant thing in the curly bracket. So the only reference to the color ordering is here, and that's a good way to verify BCJ and KK relations. Okay. Yeah, so this is the endpoint amplitude for the open bosonic string. And I should confess it's a conjecture beyond 7 points. So this integral reduction, as I said before, is quite tedious and calls for computer work. Up to and including 7 points, we went through this and checked every appearing integral to fit into that basis, and we are still trying to cook up a good math argument why it's bound to work forever. So this is the framing conjecture in which the universality statement is made. But yeah, coming back to universality, how does this amplitude result imply the claimed universality? Let me go carefully through this argument. Why universality? So we have seen that in both open string theories, the answer for the string amplitude is a product of these f functions of uniform transcendentality, where the multiple zeta weight correlates with the alpha prime power. And now the decoration is theory dependent. So either it's a pure Yang-Mills or the supersymmetrized version, if the theory is the superstring. And otherwise, it's A Yang-Mills plus pollutions with alpha prime to the k plus some non-universal kinematic factors. So the universal part of the amplitude expressions is that one. So if there's anything universal, then it's the contribution of these guys. Whenever the non-universal BKs drop out, I have identified a universal term in the amplitude and therefore in the effect of action. And what's another way to phrase this? Don't touch the BKs. If you're not allowed to touch the BKs, then you take all the alpha primes from the integral. But the integral in turn has that uniform transcendentality property, where the alpha prime order matches the MZV weight. So this basically finishes the proof or the evidence for the universality statement in the open string sector, the gauge sector. Again, the disclaimer is that this integral reduction goes through forever beyond 7 points. Okay, in view of the advanced time, I'll try to streamline the statements for the closed string. Let me do a superposition of the promised chapter 4 and 5. Let me give you the expression for the n-graviton tree, or, if applicable, multiplet tree, including various gravitinous Ramond forms and so on. So, how do the open string trees propagate to the closed string? The opening line is certainly the KLT relation, saying that I have to take bilinears in open string subamplitudes, glue them together with appropriate sign functions, and on these grounds, it won't surprise you that I can always express the closed string amplitude in the following form. All the kinematics will be captured by bilinears of the Young-Mills tree, if the theory is maximally supersymmetric. Oops, A and B. So stick in the open superstring amplitude in the KLT formula, then you will find DCJ basis of A Young-Mills with some permutations, sigma and rho. Now let me tell you a few simplifying features of the accompanying integrals. So the KLT relations involve a couple of sign functions from the monodromy games, but they also involve some multiple zeta values which you don't see in the final answer. So there are certain conspiracies between f, then sign functions, and f. You find the 4-point example of KLT on this blackboard. There's a sign function in between two open string subamplitudes, and if you carefully scan through all the orders in alpha prime, you will find that only odd zeta values appear. So there are some simplifications that KLT doesn't manifest. So that we therefore quote the endpoint generalization of that. So this has been examined in the 2012 paper with Stefan Stieberger. What you get is the field theory KLT matrix times a very simple matrix G, so this is field theory KLT, and now this G matrix contains the promised simplifications. Let me make that clear by giving the alpha prime expansion. If you now go through different orders of G in the same way as we did it for the Fs, let's track all the different zeta values that appear. There's the first zeta value is zeta 3, since zeta 2 drops out, and it turns out that the coefficient of zeta 3 is the same M3 matrix which we have seen above in the open string. This is not particularly obvious from what I gave you. It's mostly quoting the result of this paper. And also, in the field theory limit, the leading order is the unit matrix, since you want to land on the supergravity amplitude in that case. Okay, and to just give a few more terms, there is a 2 zeta 5, and again the M5 matrix. There is some zeta 3 square at weight 6, again with the matrix product of 2 such M2 matrices. And if you really want to see a higher depth multi-zeta, weight 8 is not enough, because that double zeta will drop out as well. And the first instance of a non-trivial multi-zeta is at weight 11 with such a commutator of matrices, which again drops out from the 4-point case where everything is scalar. Okay, so as before, as for the open string, with each order in this amplitude contribution, you can read off certain effective operators. So this is again the signal for Einstein-Hilbert, or the supersymmetrization to generate a supergravity tree. Then this guy, the M3 matrix, carries the tensor structure of the R⁴ operator if you combine it with the theory-dependent things. Now here M5 is already a more complicated operator, D⁴ R⁴, plus by the nonlinear tail of supersymmetry, you will also have some R⁵, R⁶ admixtures plus superpartners as usual. That guy here would start like D⁴ R⁵ plus ... all the way to R⁴. Okay. So in view of the universality statements, the important property is we again have uniform transcendentality. So schematically, I can make the same insertion as above. This is something like alpha prime to the m and some multiple zeta value of the same weight. By the way, the selection rule has a nice name in mathematics. It's the so-called single-valued multiple zeta values. So the selection rules which we observed here were later on identified by Stefan Stieberger with what mathematicians call the single-valued projection. The idea is multi-zetas in general descend from polylogs, but polylogs will usually have branch cuts and multi-valuedness. But if you only allow single-valued polylogs to land you on multi-zetas, you get fewer, namely those which you see here. Zeta 2 doesn't appear because you can't get it from a single-valued polylog. Okay, but nevertheless, it doesn't alter the main message. It's uniform transcendentality at the G's. And now, all the other alpha primes, well, the type 2 superstring doesn't have other alpha primes. And now, the less supersymmetric string theories, they will have a controlled appearance of alpha prime. Say we are interested in the heterotic string. Whoops. In the heterotic string, the kinematic decoration will be A Young-Mills plus the B case. If the theory is the heterotic one. And if you're in the bosonic string, you just take 2 copies of this extended kinematic factor. And let me emphasize again, the alpha prime dependence of B is purely rational. So both here and there, you don't see any multi-zetas. Oh yeah, and I should have finished writing here that the last line applies to the closed bosonic string. Okay, so what do we see? The kinematic decoration has a universal part. In all of the theories, you will have the quadratic expressions in Young-Mills trees. So this is an identical alpha prime to the 0th order for these 3 closed string amplitudes, and we can carry out the same sort of argument as for the open strings. Namely, the universal terms are those where neither the left mover nor the right mover contributes a B. And this is one-to-one equivalent to saying that you take all the alpha primes from the G, but by uniform transcendentality of the G, this means that in the universal alpha prime terms, you have a correspondence between the alpha prime order and the transcendental weight of the multi-zetas. So this finishes the argument for the universality result in the closed string sector. And as you can see, it some sort of follows as a corollary of KLT. Once you have made this argument sharp in the open string side. So is the flow of the argument clear, or are there parts that I should repeat? If not, then let me repeat the words that I said earlier on as a reply to Louise's question, to ask about implications for the big picture. These are a couple of effective operators that want to appear in all the string theories, and if you meditate about string theory being a candidate for quantum gravity, this might be a window to see or to probe some universal features of quantum gravities. But I guess it's only a very small window, and it calls for way more evidence, which we hopefully obtain in the near future. Okay, thank you very much for your attention.
Okay, so in view of the time, maybe only urgent questions. A little bit of an urgent question.
So the mass you throw out, is it just due to the tachyon, or also to higher mass states you find in the bosonic string you wouldn't have in the?
You mean propagators of this type, whether there's a -2
I
somewhere?
mean the mass that is not the same, that is not universal.
What you call B.
B. Yeah.
Ah, B, yeah, B, here. Okay, so, sorry, could you
Is it just due to the tachyon, or what about the higher mass states that you have in the bosonic string that you don't have in the superstring?
Oh, okay, yeah. Sorry, the fingerprints of the higher mass level states is, well, the zeros of and the poles of the function f, which are not at all manifest in the low energy expansion. F will have poles for all the higher mass levels. And, well, the tachyon fingerprint, it just happens to appear as an integral coefficient.
So
And
do you understand that? I mean, is it just some sort of generalization of the statement that super Young-Mills or Young-Mills amplitudes are the same at tree level?
if you project to the 0th order, then yes. And okay, beyond that, well, I called it a tachyon pole, but the heterotic string, as you know, doesn't have any tachyons. So here is a non-manifest property. You might worry here that the tachyon poles on the kinematic factor will cause you a tachyon propagation, but the above objects have zeros whenever the tachyon tries to propagate. So this is unfortunately obscured in this representation.
I'm just trying to understand the nature of these terms that are not universal, or,
Okay.
or rather to understand what's the
Okay, it's a bit doing injustice to them to degrade them to an expansion coefficient. So I understand this was maybe a bit of abusive terminology. On the one hand, it's just an expansion coefficient, which later on will be geometric series expanded. But on the other hand, it's a tentative tachyon propagation if you leave it uncancelled, like in the bosonic string theories. But it's really the technical nature of the integral reduction. You won't see any +2 or -2. This is basically all there is in intermediate steps.
If there are no other questions, let's thank Oliver again for